Okay, so today we're going to be doing some work on hypothesis testing. So this is the last chapter on the AES statistic. So a hypothesis is a statement made about the value of a population parameter, and you can test the hypothesis to see if there is enough evidence to change it. So in this chapter, it's all about testing statistically whether a statement are true or not. So there are several key terms you need to know. Population parameter. A population parameter is a statistical measure relating to a population. So for example, the mean is a population parameter. And a hypothesis is a statement made about a population parameter. Null hypothesis, H0. So it's the default position which we usually initially assume to be true. For example, a null hypothesis would be, if you think about a courtroom, everyone's innocent until proven guilty. So the default position is you're innocent if you go to a courtroom. So this is the null hypothesis. The null hypothesis would be if you flip a coin, that it's going to land on head is 50-50 chance. So these are what we call the null hypothesis. If you're rolling a 6 on a die, null hypothesis would be P equal to 1/6. An alternative hypothesis. So this one, it tells us the hypothesis is about the parameter or the situation if our null hypothesis turn out to be incorrect. So if our null hypothesis is incorrect, what are the alternatives? So for example, if you're rolling a dice and getting a 6, then alternative hypothesis would be P not equal to a 6. A test statistic. A test statistic is the result of the experiment we are using, which we use to test the null hypothesis. So if we toss the coin 4 times and we got 3 heads, then the value or proportion is the test statistic. So let us think about a more practical example. Imagine we believe that a die is biased towards landing on 6s. We rolled the dice 20 times and we got a 6 on 8 occasions. What is the test statistic for this situation? The test statistic is the proportion of 6s we got from the 20 rolls. So now we're going to write the null hypothesis for this situation. So the default position would be the dice is not biased. So the null hypothesis, we write H0 and then we put colon P probability equal to a 6th. So that's the null hypothesis. Now the alternative hypothesis, so our belief is the dice is biased towards landing on a 6. So the alternative hypothesis, this time you have to be very careful because the null hypothesis was P equal to a 6. The alternative hypothesis is P is greater than a 6. Because look at the question here. Our belief is that it's biased towards 6. So it's more favorable towards 6. Therefore, we expect the probability to be greater than a 6. And this is important to understand because in this case, we're going to have what we call a one-tail test. And later on, we're going to look at when it's equal to or not equal to, it's a different kind of test. So it's very important you understand a one-tail and a two-tail test, whether it's a greater than or less than or not equal to. So in this case, it's greater than, so it's a one-tail test. So our null hypothesis is P equal to a 6. A researcher wants to test at 5% significance level whether the dice is biased. So we're testing out a 5% significance. So under what condition would we reject the null hypothesis? So what is the probability of getting 8 sixes when rolling a dice 20 times? Well, we know this obeys the binomial distribution. We have fixed number of trials. Probabilities are independent of one another. So it meets the usual binomial condition. So we could work this out. From the previous chapter, we know binomial distribution. So why don't you pause this video and work this out. So once we submit the value and calculate, we get the following: 0.0084. So very small chance. Okay, so now as a percentage, we know this is just 0.84%. So it's a very small chance, 0.84%. So as this is below the 5% significance level, we reject the null hypothesis that dice is unbiased. As this is below the 5% significance, we reject the null hypothesis that dice is unbiased. So think about why we reject the null hypothesis. We are saying that if the dice is unbiased, we would expect to get 8 sixes. It's only 0.84% of the time. As this is extremely unlikely, it seems like the dice is biased. Hence, we reject the idea that it's not. Imagine we had rolled 7 sixes instead. So probability of 7 sixes, doing the same thing on the binomial, and you could plug this in the calculator, we get 2.5%. So as this is below 5% significance, we reject the null hypothesis. Again, we say this dice is biased because 2.5% is less than 5%. So rolling a 7 sixes out of 20 also indicates the dice is. So imagine we rolled 6 sixes instead. So what I'd like you to do is pause the video and work out the probability of getting 6 sixes. So here, probability of getting 6 sixes is 6.4%. Well, that's different, isn't it? Because 6.5%, sorry, 6.4% is greater than 5% significance. So therefore, we cannot reject the null hypothesis. So our conclusion would be, we cannot reject the null hypothesis that dice is unbiased. Although getting 6 sixes is unlikely, we are saying that it is not unlikely enough to reject the idea that dice is biased. So let's have a look at this. Good. So John wants to see whether a coin is unbiased or whether it is biased towards coming down on heads. He tossed it 8 times and he counts the number of times x that it lands on head. So we've been asked to describe the test statistic, write down a suitable null hypothesis, and write down a suitable alternative hypothesis. So the test statistic here is that number of heads we get from 8 tosses. So when you say describe the test statistic in the test or in the exam, you would write something like this. So the test statistic, what are you testing? We're saying the test is on the number of heads we get out of 8 tosses. So in this case, the default position is we expect the coin to be probability of half of landing on head. So H0, P equal to half. The alternative here, remember John's opinion is the coin is biased towards head. So in this case, the alternative would be P greater than half. If it did not specify whether he believes is biased towards or not, then it would be a two-tailed test. We will say not equal to half. So that's something to remember, whether he believes it's biased towards head or he thinks it's biased. So these are two different cases where you have to be careful how you read this. So let's have a look at this example here. So here we're told an election candidate believes she has support of 40% of the residents in a particular town. A researcher wants to test at 5% significance level whether the candidate is overestimating her support. The key word here is she is overestimating her support. So the researcher asked 20 people whether they support the candidate, and 3 of them say they do. So first we are asked to write down the test statistic, then B, null hypothesis, and then where it says write down the suitable hypothesis. So in this case we need to write down both the null and the alternative hypothesis. And C, we are asked to explain the condition under which the null hypothesis will be rejected. So for the test statistic, you would say the test statistic, the number of people who say they support the candidate. So the default position, P is equal to 0.4 or 2/5. The alternative is P is less than 2/5 or 0.4. So in this case, the null hypothesis will be rejected if the probability of 3 or fewer people saying they support the candidate is less than 5%. So in this section, we are going to consider the testing the probability the dice was biased and calculate the following data. So probability getting 6 sixes out of 20 is 0.064. 7 sixes out of 20 is 0.025. 8 sixes out of 20 is 0.084. So let us put this in a table and fill in some more data. So if we have a table like this, so X is the number of sixes from 20 throws, and here are the probabilities. We can draw this information, and we could get this from our calculator, the scientific calculator, and we could represent this graphically. Remember, these are discrete data, so it will look something like this. You cannot join them because these are discrete values. So this is looking at number of sixes out of 20 throws. So originally we were considering whether the dice was biased towards sixes at 5% significance level, and this can be represented on a diagram. So if you see this dotted line here, this is at 5% significance level. So from this dotted line, anything below, we would reject the null hypothesis. And we've seen how previously 7 and 8 we rejected if we got it 7 times or 8 times. So we say these are the critical value. 7 is the critical value. Because 7 or more, we will reject the null hypothesis. So the critical region would be the set of values that would lead the null hypothesis being rejected. So in this example, any number of sixes equal to or greater than 7 would be rejected. So this is the critical region. So the critical value is 7, but this bit here we say is the critical region. So anything in this region, the null hypothesis will be rejected. Here we were only considering whether the dice is biased towards sixes. So if we were just considering whether the dice is biased, we could also include the value of 0, because that would also be in the critical region. So this is another critical value. So this is indicating that if we did not get any sixes from the 20 throws, then the dice might be biased against sixes. instead of towards. And in this case, we say these are two-tailed tests, and we will see more about that later in the chapter. So for one-tailed test, we are interested in these two values. For a two-tailed test, we're interested in both the left-hand side and the right-hand side. So here's an example. So here we're told a single observation is taken from binomial distribution B, trial 6, probability P. The observation is then used to test at H0, P equal to 0.35 and alternative P greater than 0.35. And we asked, using a 5% significance level, find the critical region for this test. B, state the actual significance level for this test. So the null hypothesis, P equal to 0.35. So assuming H0 is true, then X approximates to binomial distribution with trial of 6, probability 0.35. You can use your calculator or use the statistical table to find out for which value of the probability is less than 5%. So this is the table that is in your formula booklet, and you're given this in the exam. So we go for trial of 6, probability 0.35, and from here, so this is the section that we're interested in, we need to check these values. As always, think about what the numbers mean. So this number here, 0.8826, means there are 88.26% chance of the number of success being less than or equal to 3. So therefore, it also means that 11.74% chance of getting 4, 5, or 6. So it negates the idea. It's the other side of the argument. So this is not unlikely enough to reject the null hypothesis. The probability is 0.35. So we look at the next value. So 0.9777 means there are 97.77% chance of the number of success being less than or equal to 4. So therefore, there are 2.23% chance of getting 5 or 6 success. So this is unlikely enough to reject the null hypothesis. The probability is 0.35. So that means the critical region is therefore 5 or 6. So this is the critical region, 5 or 6, or sometimes you could just write greater than or equal to 5. So think about it in context. If it does not have one in the question, you can think of this as playing a game 6 times, and we assume that there is a 0.35 chance or probability of winning each game. So we just saw the chance of winning 5 or 6 games is 2.23%. So if this happens, we reject the null hypothesis because it seems like actually the probability of winning is higher than 0.35. The actual significance level is the probability of the test statistic falling within the critical region. It can also be thought of as the probability of incorrectly rejecting the null hypothesis. We've already found the critical region in part A. In this case, the chance of getting 5 or 6 successes can be calculated as follows. We could say the probability of x greater than or equal to 5 is 1 minus probability x less than or equal to 4. So probability x greater than or equal to 5 is 1 minus 0.9777. which gives us 0.0223. So the actual significance level, we would say, is 2.23%. So it's important you understand the difference between the critical region and the actual significance level.